All right, this is our discussion of Chapter 2, which is an introduction to basic chemistry. And one of the things we need to point out is that it's important to understand chemistry because a lot of what goes on in the human body involves chemical interaction. Okay, so we're going to talk about the building blocks of matter, which are called atoms. We're going to talk about how atoms connect to each other, which is called chemical bonding. And then we're going to talk about important molecules in the body. We'll talk about different types of chemical bonds. We'll tell you what an ion is. Okay? So matter is anything that occupies space and has weight. And matter comes in three states: solid, liquid, and gas. And these states differ in terms of how much movement there is in those states of matter. In the solid, the particles that make up the solid don't move very much. They just sort of stay in one spot and they vibrate a little bit, and that's why a solid doesn't change its shape. Okay? A liquid has particles that move past each other. All right? And so a liquid can form to the shape of its container. So it has more kinetic energy than a solid does. That's energy of movement. And then a gas has particles that move even quicker. And as a result, a gas can touch every part of the container that it's in. Like the air in the room you're in right now touches every wall, the ceiling, the floor, everything. Okay? So it has even more kinetic energy. Now, when the universe was made, there were only three things that made up the entire universe, and that's matter and energy and empty space. Okay? So empty space is nothing but empty space. Energy is the ability to do work, and matter is anything that occupies space and has mass. So essentially, the way that the universe operates is under two laws, and they're called the first and second laws of thermodynamics. Okay? And the first law of thermodynamics is pretty easy. It says that energy and matter can't be created or destroyed. And the second law of thermodynamics says that for any system we consider, which could be the water in a glass, or the air in a room, okay, or the dust in your house, if you don't put any energy into the system will try and find the lowest energy state to exist in. So another way of saying that is things tend to take the easy way out, right? So as long as we obey those two laws, we can understand how it is that chemical reactions take place. Okay? Matter comes in a lot of different forms, right? We talked about solid, liquid, and gas. Well, the same is true of energy, right? Energy can be mechanical energy, which is the energy to move stuff. It can be electrical energy, which is the movement of charged particles. It can be chemical energy, which is the making and breaking of chemical bonds. It could be kinetic energy, which is the energy of movement. Okay, every time that something energetic happens, some of that energy gets lost as heat, and that heat goes off and makes the universe more random, or a chemist would say that it increases the entropy of the universe, and that's a measurement of what we call disorder. Okay? Physical changes are simply changes that result from mechanical action on a substance, and they don't alter the way that the building blocks of matter are connected to each other, while a chemical change rearranges the way that the building blocks of matter are connected to each other. Okay? An element is matter composed of identical atoms which have the same number of positive charges in the center of the atom, which is called the nucleus. Okay? And the human body is composed of elements. All right? The major elements in the human body are oxygen, carbon, hydrogen, and nitrogen. And then the other elements that are found there are called trace elements. Okay? So those are the major elements. Okay? By by percentage body weight. And then the trace elements would be things like calcium and iron and nickel and magnesium. But they're still important, right? If we didn't have these trace elements, then we wouldn't be able to function properly. For instance, if I were able to magically remove all the iron from your body, you would die because you wouldn't be able to carry oxygen in your blood bound to a protein called hemoglobin, and you wouldn't be able to make a form of energy that cells need in order to function, which is called ATP. The smallest unit of an element that still has the chemical properties of that element is called the atom. Okay? An atom is an ancient concept. It goes back to the ancient Greeks when a gentleman named Democritus was one day looking at a boulder, and he determined that if he took that boulder and he broke it in half, he would have two smaller boulders, but they would still have the same property as the original boulder. And if you repeated that process, he would have four even smaller boulders. Then he reasoned that if he kept continuing to do that, that he would eventually get to a point where he couldn't divide those particles any tinier and still have them have the property of the original boulder. And he called that particle the atom. Okay? And that's really the working definition of the atom that we have today, right? The smallest piece of an element that still does the same chemistry as bigger quantities of the element. So this is a little look at the organization of atoms.
An atom is the smallest particle of an element that retains the properties of that element. Atoms are composed of smaller particles called protons, neutrons, and electrons. The central nucleus contains protons and neutrons, while electrons move constantly around the nucleus in concentric regions called electron shells, or energy levels. A proton has a single positive electrical charge, and an electron has an opposite negative charge. Neutrons are neutral, with no electrical charge. Each element is uniquely defined by the number of protons in an atom of that element. For example, only carbon atoms have 6 protons, and only potassium atoms have 19 protons. The atomic number is the number of protons in an atom of a particular element. The number of protons equals the number of electrons, making atoms electrically neutral. Electrons are so small that they have almost no weight. The atomic mass is the sum of an atom's protons and neutrons. The number of neutrons in a particular atom, and thus atomic mass, can vary. Atoms that have the same atomic number but different atomic weights are called isotopes. Electrons occupy electron shells in fixed numbers. The first shell, closest to the nucleus, holds a maximum of 2 electrons. The second shell holds 8 electrons, and the third shell can hold up to 18 electrons. Subsequent shells can hold higher numbers. The outermost shell, known as the valence shell, holds a maximum of 8 electrons. The electrons in the valence shell determine an atom's chemical bonding properties. Atoms such as helium, whose outermost electron shells are filled, have stable structures and are chemically inactive. Atoms with partially filled valence shells tend to lose, gain, or share electrons to either empty or fill their outer shells, producing a stable number of valence electrons. The number and kind of bonds an atom will form depend on the number of electrons needed to fill the valence shell.
So as you can see, the atom is a particle made up of tinier particles. The atom has a region in the middle called its nucleus, and it has a region outside the nucleus which are called orbitals, and that's where electrons reside. Electrons have a negative electrical charge, and they move around the nucleus at the fastest speed anything can move, which is the speed of light. Okay? The nucleus contains particles like protons and neutrons. Okay? The protons have a positive electrical charge, and the neutrons have no electrical charge. And in any atom, the number of protons and the number of electrons is always the same. And so there is no net electrical charge in an atom. Okay? You can see here an example of an atom. Okay? Here you've got an atom that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total electrons. Okay? So this would represent an atom that doesn't do any chemistry because all of the electron shells are filled up. Okay, the first shell can host a maximum of 2 electrons. The next shell can host a maximum of 8 electrons. And the reason that atoms that have a full shell don't do any chemistry is because they're in a low energy state. So they obey the second law of thermodynamics, which states that you try to get to a low energy state any way you can. Since these atoms are already in a low energy state, then they don't really have to do anything else. Okay? And this happens to be an atom of neon. Okay? So, what about the rest of the atoms? Well, the rest of the atoms exist in a state where the outer shell is incomplete. Okay? And in order to get to a low energy state, they either try to share or give up or pick up electrons from other atoms. And when they do that, they form associations with each other that are called chemical bonds. Okay? The atomic number of an atom is the number of protons in the nucleus, and it always identifies the type of element, where the atomic mass is basically the sum of protons and neutrons in the nucleus of an atom. But often when you look at the atomic mass, it's a little bit heavier than you would think, because some of the atoms that were made for each element when the universe was created had some extra neutrons in the nucleus, and as a result the average mass of a collection of atoms is a little bit higher than you would think. Okay? But just because an atom is a little heavier because of the extra neutrons does not affect the way that it does chemistry. An isotope is just a version of an atom that has a different atomic mass because it has more neutrons in the nucleus, and it does the same chemistry as the lighter versions of the same element. Why do we care about isotopes? Well, because some isotopes actually give off energy, okay? And when they do that, they are able to have that energy traced, okay? For instance, some isotopes give off X-rays, some isotopes spit out electrons, and some spit out protons, what we call alpha particles, okay? And that energy can be tracked. It can expose, for instance, photographic film, or we can pick it up with a detector. And so when we put these types of atoms in a compound that the human body uses, we can determine where that compound goes by looking at it through something that can detect where the radioactivity is coming from. And that tells us about how those organs and tissues are working without us having to open you up. Okay? An example would be X-rays, right? X-rays are a type of radiation that's given off by isotopes that are radioactive, and X-rays can pass through soft tissue real easy, but hard tissue it doesn't pass through real easy. And so when you run X-rays through, say, a broken arm or a broken leg, okay, the radiation will stop when it hits bone, but it'll pass right through stuff like skin and muscle. And so on the X-ray film, the bones will look white because the film wasn't exposed there, and the area with the bones and muscles will look grayish. Okay? That's just one example. In an atom, there are certain regions where the electrons can exist, okay, and they're called shells. And the first shell can hold 2 electrons, the second shell can hold 8, and the third shell can hold up to 17, but it's happy with 8. Okay? A full shell means a stable atom. All right? And so any way that an element can fill up its shell, it'll try to do that. The number of electrons in the outermost shell determines the type of chemical bonds and the number of chemical bonds that an element can form. Okay? A chemical bond is just the attraction between atoms. There are connections between atoms, and there's three types: covalent, hydrogen, and ionic. So let's take a look at ionic and covalent bonding.
When forming compounds, atoms tend to gain, lose, or share electrons to achieve a stable noble gas electron configuration, an octet of electrons. In ionic bonding, an octet is formed by transferring one or more valence electrons from one atom to another. In covalent bonding, an octet is formed by sharing valence electrons between atoms. Sodium has one valence electron and fluorine has 7 valence electrons. If the one valence electron of sodium is transferred to fluorine, both atoms achieve an octet of electrons. By losing one electron, sodium has a +1 charge. By gaining one electron, fluorine has a -1 charge. An ionic bond is the electrostatic force that holds ions together in ionic compounds. Both fluorine atoms have 7 valence electrons. If one electron from each fluorine atom is shared with the other atom, then both fluorine atoms achieve an octet of electrons. This type of bond is called a nonpolar covalent bond. The sharing of electrons between atoms is exactly equal, and the electron density is symmetrical. The distribution varies according to the colors of the rainbow. The most electron-rich region is shown in red, in this case the region between the two nuclei, and the most electron-poor region is blue. Hydrogen has 1 valence electron and fluorine has 7 valence electrons. If the 1 valence electron of hydrogen is shared with 7 valence electrons in fluorine, fluorine achieves an octet of electrons. Note that hydrogen has only 2 electrons, which is the electron configuration of helium. When bonded to another element, hydrogen will have 2 electrons in its valence shell. In this bond, fluorine has a greater attraction for the electrons in the bond, a greater electronegativity. Because the electrons spend more time near the fluorine atom, the electron density shifts towards fluorine. The most electron-rich region is red. The most electron-poor region is blue. The result is a greater electron density near fluorine, a partial negative charge, and a correspondingly lower electron density near hydrogen, a partial positive charge. This type of bond, where bonding electrons are unequally shared, is called a polar covalent bond. A polar covalent bond can be thought of as an intermediate between a nonpolar covalent bond and an ionic bond.
What you're looking at here is the formation of an ionic bond. Okay? Ionic bonds always form between metals and nonmetals. Okay? There's a chart that I'll show you in a minute called the periodic table that shows all the elements in the universe. And the nonmetals lie primarily on the left-hand side of the table, and the metals lie on the right-hand side of the table. And the table is arranged in rows and columns. The rows are called groups, and the columns are called periods. And the columns basically each contain members that have the same number of electrons in their outer shell. Okay, so that's what determines who belongs to a particular group. Okay, and a period is just an increase in atomic weight as you go from left to right across the table, and we'll see all of that in just a minute. So you can see here an example of a sodium atom, right? A sodium atom has 1 electron in its outer shell because its atomic number is 11, right? It's got 11 protons here, 2 in the first shell, 8 in the next shell, okay, for a total of 10, and then the 11th electron is out here. Well, that doesn't represent a full outer shell, and so that represents a high energy state. And we know from the second law of thermodynamics that we want to get out of the high energy state whenever we can. So when it meets up with a chlorine atom that has 7 electrons in its outer shell, it would like to complete that outer shell by picking up 1. So what will happen is that the sodium will donate one of its electrons to the chlorine. By doing that, the sodium atom loses a negative charge, and the chlorine atom gains a negative charge, and they become what are called ions. Okay, the sodium becomes a cation over here, and the chloride anion forms over here. All right, and what holds them together is the fact that they have opposite charges. Opposite charges attract, just like opposite poles of a magnet attract. Okay, ionic bonds tend to be a little bit weaker than the other type of bond we're going to explore, which is a covalent bond. Okay, but they usually form between metals and nonmetals. Okay, when nonmetals chemically react with each other, they form a type of bond called a covalent bond, in which electrons are shared. All right, and an example of that is here. Okay, this is an example of an oxygen atom. Oxygen is a nonmetal. Okay, hydrogen in this case is acting as a nonmetal, and what happens when they associate with each other is that they share pairs of electrons. The oxygen has 6 in its outer shell, and so it can pick up 2 to complete it, and the hydrogen has 1 in its outer shell and can pick up 1 to complete that shell. And so when they form water, H2O, if we count the electrons, you can see that for oxygen we have 1, 2, 3. Let me get the pen up here. And we'll do an arrow. Right? Okay. So you can see 1, 2, 3, 4, 5, 6, 7, 8 electrons in the outer shell. Okay? That's a complete outer shell, and that means that the oxygen is stable. Okay? Look at the hydrogens. 2 in the outer shell here, and 2 in the outer shell here. Okay? Now the sharing in this case isn't quite totally even, and the reason is that the oxygen has a property called electronegativity. Okay? When we look at the periodic table, you're going to notice that the electronegative atoms are the ones to the right of carbon and to the left of the last column in the periodic table, and they have greater electron pulling ability because of their greater positive charge, and there's less blocking of that charge by the electrons than the hydrogen does. And so these electrons actually spend most of their time with the oxygen and some of the time with the hydrogen. So we call that a polar covalent bond. Another type of covalent bond is a nonpolar covalent bond. And nonpolar covalent bonds form when 2 identical atoms attach to each other, okay? Or when you have a connection between carbon and hydrogen, all right? And those bonds have an almost perfectly equal distribution of electrons between the 2 atoms that participate. And the significance of that is that in molecules that have polar covalent bonds, they tend to mix or associate or do chemistry with other molecules that either have polar covalent bonds or have ionic bonds. And the reason for that is that since there are ends to the molecule, one end that is more positive and one end that's more negative, they can associate with the more positive or more negative end of another molecule, and as a result, they can approach each other more easily. Okay, in an example of sodium chloride, right? The ion here, sodium chloride, that's table salt. Okay, and it comes as a little crystal. And if you look at a crystal of table salt, what you would see is a cube. All right, and if we could get down to the tiniest atomic level and look at that cube, what we would find is that the positive ions are surrounded on all sides by negative ions, and the negatives are surrounded on all sides by positives. When you drop that cube into water, all right, here, what happens is that the water interrupts the attachment between the anion and the cation by sticking its say, oxygen between the two participating ions, and then the ions fall off the cube and they dissolve. Okay, and so they're surrounded by water molecules that do what's called solvation. All right, so they're not associated in a crystal anymore, they're just kind of floating free. And that happens without having to add any energy to the system. It just happens automatically. All right, so let's real quick take a look at the periodic table so that you can have an idea of what I'm talking about, and then we'll move into a discussion of hydrogen bonding. Okay, what you're looking at here is a periodic table, all right? And this is a list of all the elements in the universe, right? These are the columns. Let me get an arrow going here. Okay, these are the columns, which are called groups, right? And these are the rows that are called periods, all right? And this little stair step that you see here is the dividing line between the nonmetals, which are over here in kind of silver, and the metals, which are here in green and yellow and orange and over here in gray. Okay? So when metals react with each other, they form what are called metallic bonds. Okay? And that's beyond the scope of this course. When metals react with nonmetals, they form ionic bonds. Okay? And then when nonmetals react with each other, they form covalent bonds. And remember, I was telling you about electronegativity, right? The ability in a covalent bond to pull electrons towards you more strongly. Well, here's carbon, right? Everything to the right of carbon, so nitrogen, oxygen, all of these guys, which are called the halogens, okay? Sulfur, phosphorus, all of these guys are electronegative. And so if they're in a compound along with carbon, then they're going to form polar covalent bonds, all right, which means that they'll more easily associate with other polar or ionic compounds, because that's, again, obeying the second law of thermodynamics, which is try and arrange things in the lowest energy way, okay? You can also see that the little boxes here tell you about the elements, right? The letter symbol is the symbol for the element, and the number on the top is the atomic number, and that's the number of protons in the nucleus. And the numbers on the bottom here, the littler numbers, that's the atomic mass. And you'll notice that for most of these elements, it's not a nice round number. Like here in carbon, it's 12.01. And we talked about the reason for that being that some carbon atoms are a little heavier than others because they have extra neutrons in their nucleus, so they're what are called isotopes. And as a result, when you take the average weight of a collection of carbon atoms, it's heavier than you think. Okay. The way that a chemist uses this is that he can look at that number 12.01, and that represents the number of grams that 1 mole of that particular element weighs. Okay. A mole is just a count, just like a dozen is 12. A mole is 6.02 times 10 to the 23rd of whatever we're talking about. Okay. And so that's how a chemist can use these weights to determine how many atoms of something he has when he weighs out a certain amount of it. Okay, just wanted you to know that. And then this column over here, these are the elements that don't do any chemistry, and that's because they have full outer shells. Helium has 2 in its outer shell, and the rest of these guys have 8. Okay, and that represents low energy. Okay, so that's essentially the information available from the periodic table. I just wanted you to get a look at it. Okay, the next thing we want to discuss is hydrogen bonding. So you'll want to take a listen to this.
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
So as you saw in the previous video, hydrogen bonding is a weak association between molecules that have partially positively charged hydrogen atoms in their structure and other atoms that have partially negatively charged atoms in their structure. Okay, with water, the partial negatively charged atom happens to be oxygen. Okay, and that has a short attraction to hydrogens that are nearby, and that provides for things like surface tension and capillary action, the fact that water can wick up a paper towel because it's a polar compound, and the paper towel is made of a polar compound called cellulose, and so they're attracted to each other. Okay, hydrogen bonding can also happen between other electronegative atoms. For instance, nitrogens, okay, can attract hydrogen, so you can have hydrogen bonding there. That's actually one of the things that holds DNA together. Okay, next thing we want to talk about are ions. Okay, ions are just charged atoms. Okay, so atoms that have either gained or lost electrons. Cations are positively charged, and the way I remember that is that the T in cation looks like a plus, and anions are negatively charged, and they are attracted to each other. They form what are called electrolytes when they're dissolved in water, and the reason we care is that electrolytes can conduct current. Okay, when charged particles move, that's a form of electrical energy called current, and that can be used to do work. Okay, nerve cells use it to send electrical signals around the body, so that we can do things like send commands to our muscles and move. And muscle cells use it to eventually contract, and then every cell in the body uses it to help it move stuff across its outer barrier called its cell membrane in order to get stuff it needs inside and pitch stuff that it doesn't want outside. Okay, you can see some examples of some important ions here, all right, and what they're used for. This is table 2.2 in your book. Okay, some more ions here. Okay, this is just showing you what I was talking about earlier, what happens when you throw an ionic compound into a polar solvent is that the polar solvent will essentially dissolve the ionic compound so that the ions float freely in the water, and they're surrounded on all sides by the solvent, and they move, and that allows them to do things like conduct current. Okay, it also allows them to determine where water goes. One of the things you're going to learn about in the next chapter is a type of cell transport called osmosis. And the way osmosis works is that in a water-based solution, any solution that contains stuff dissolved in it, like sodium chloride for instance, will attract pure water to it from another location if the concentration of water in that location is higher. Okay, so that in the body determines to a large extent where water goes in the body. In our next lesson, we're going to talk a little bit about some different compounds. We'll talk about pH, and we'll talk about enzymes and catalysts and ATP, and talk about mixtures. Okay, remember that a molecule is basically 2 or more atoms connected to each other in some order. Okay, They could be the same atom or they could be different atoms. Okay? A compound is when two or more different atoms are connected to each other in some order. Okay? Um, in in a molecule where the atoms are the same and they're connected to each other, if it's non-metals that are attached to each other, or even if it happens to be metals, the sharing of the electrons is going to be equal, right? And so there won't be a separation of charge across that molecule. Whereas if the participating um, atoms are different, all right, then in most cases there's going to be unequal sharing of the electrons, except in the special case of carbon and hydrogen. Okay? Now, water is absolutely critical for life for several reasons, right? It's called the universal solvent because ionic compounds and polar compounds dissolve very easily in it. The way to think about this whole thing with polar and nonpolar is that like dissolves like, okay? So a nonpolar thing will dissolve in a nonpolar thing without adding any energy, and a polar thing will dissolve in a polar thing, and an ionic thing will dissolve in a polar thing, okay? And that, again, is just plain old second law of thermodynamics, right? Things that are similar in their chemical characteristics like to associate with each other, right? An example of this is a bottle of Italian salad dressing, right? When you pull it off the shelf, the oil, which is nonpolar, is on the top, and then all the rest of the stuff, the spices and the water and the seasonings, are on the bottom, okay? And those tend to be polar or ionic compounds. If you take the bottle and you shake it, you add energy to that system, and you form a temporary mixture called an emulsion. But then if you set the bottle down and you wait for a period of time, the oil and the rest of the dressing will separate like it did before, and that's it, assuming it's a low energy state. Nonpolar associating with nonpolar, and polar or charged associating with polar or charged. Okay? And again, second law of thermodynamics, right? Right there in the grocery store. It's a temperature regulator. Because of hydrogen bonding, water can give off or absorb a lot of heat without changing temperature very much. And that's important because it helps to regulate changes in our body temperature. We're mostly water, okay? It's a lubricant. It's important because chemical reactions can happen in it. Since it dissolves a lot of stuff, and since it's a liquid, that means that a lot of stuff is in there and it's moving around. And if it's moving around, it can bump into other molecules, and then that can make chemistry happen, okay? And it also provides a degree of protection for the human body. And it's also frequently a participant in chemical reactions, okay? Water can be used to split long chains of molecules into tinier pieces, and that's a chemical reaction called hydrolysis. And it can be used, it can be removed from chemical units that have the components of water in them, OH groups and hydrogen groups, and you can form long chains, and that's something called dehydration synthesis, and we'll see that in a bit as well. Okay? Oxygen is critical to life. It's 20% of the air that we breathe, and the reason we need oxygen is because in the presence of oxygen, we make 20 times more usable energy than we do without it. If we didn't have oxygen around, we wouldn't make enough energy to survive. So a biologist would say that we are obligate aerobes, right? We have to breathe oxygen in order to live, okay? Carbon dioxide is a compound that is generated as a waste product of a series of reactions called metabolism, okay? Metabolism are basically all the reactions that compose life, okay? And if carbon dioxide is allowed to build up inside our body, it'll create toxic conditions that'll kill cells and tissues, which is why we have to exhale it in our breath, and we also lose some of it in our urine as an ion called bicarbonate, okay? And we lose some of it in our sweat, and it's carried around in our blood too, okay? That's how it gets from the tissues in our body to an exit point, all right? A chemical reaction is simply an association between two things that collide with each other or that come apart. On the left side of a chemical equation are what are called the reactants. Those are the things that are getting together. And on the right side of the chemical reaction are the products, and that's what you make. Okay. Now, chemical reaction relies on a collision to happen. Okay. If we were to sketch a chemical reaction, let's make a pen here, and do a pen, and we could have a hypothetical set of reactants, right? Like we could have A, and we could add that to B, okay, and then we would produce C, okay. In order for this to happen, A has to bump into B, okay. The more often that A bumps into B, the more C that we'll make, okay. So one of the ways that you can speed up a chemical reaction is to increase the amount of the reactants, right? The more reactants that are in the reactant vessel, then the more of the product you're going to make. Another way to increase the rate is to warm the reaction up. By warming a reaction up, you have more movement. When you have more movement, you have more collisions, and you make more of the product. All right. The problem with that is that if you try to do that in a living cell, you probably kill it. Okay. If we were to say dramatically increase the amount of A or B, all right, we would create conditions that would probably draw water into the cell at such a great rate that the cell would swell up and rupture. Okay. If we were to warm the cell up, we would probably cook it, right? We would destroy the molecules that sustain life, which are called proteins, and the result is the cell would die. So how is it that we can do the chemical reactions that sustain life quickly enough to keep all the cells and tissues doing their job? And the answer comes from what are called catalysts. All right, a catalyst is simply some molecule, or in some cases it's even an element, all right, that speeds a chemical reaction up by making the collisions that produce the product always be effective and easier to happen. Okay, so it's like a catalyst comes into a chemical reaction and sort of grabs the reactants by the neck and says, y'all are getting together to make the product whether you want to or not. And then the catalyst can then turn around after it does that and catalyze another reaction. So when you throw a catalyst into a chemical reaction, it happens very quickly, and you don't have to play around with the temperature or the concentration. Enzymes are biological catalysts, and they are proteins. And what they do is they speed up the chemical reactions that sustain life. And there's thousands of different enzymes that catalyze thousands of different reactions. And so they have a property called specificity, meaning they only deal with a particular set of reactants, and they only generate one particular product. And so just like a key only fits in one lock, okay, an enzyme only does basically one reaction. And so these are all inside the cell doing the work of sustaining the cell's life. Okay? An important property that we have to keep an eye on in living systems is pH. Okay? pH is a measurement of how acidic or how basic a solution is. Right? If the solution gets too acidic or too basic, it creates conditions that'll kill the cell, kill the tissues, and then kill you. Right? An acid is any molecule that donates hydrogen ions into a solution. Okay? And when it does that, the concentration of hydrogen ions increases, and that causes the pH to go down and become more acidic. Okay? A base is a substance that scoops up hydrogen ions and causes the pH to go up. Okay? A strong acid will ionize completely, and a weak acid not very much, while a strong base will ionize completely, and a weak base won't ionize very much. Okay? So the effect on pH of a strong acid or a strong base is pretty substantial, while the effect on pH of a weak acid or a base isn't so much, okay? You can see here the pH scale, okay? The pH scale runs from 1 to 14, and it's a measurement of how many protons there are in a particular solution, okay? Neutrality is defined as 7 on the pH scale, okay? As the number of protons goes up, the pH goes down, okay? As the number of protons goes down, the pH goes up. Let me turn this into an arrow here so that we can see what we're looking at. Okay. So in this direction going down, more basic. In this direction going up, more acidic. Okay. Now, again, why do we care? Because if we get outside the normal pH range for the body, which is between 7.35 and 7.45, we'll create conditions that will cause disease. If we're below 7.35, that creates a condition called acidosis. And if we're above 7.45, that creates a condition called alkalosis. Okay? And those conditions will cause proteins to quit doing their jobs, and that includes the proteins known as enzymes. And so those chemical reactions would stop. All right? And that also causes the membrane not to function the way it's supposed to in order to transport stuff into or out of the cell, because it ruins an electrical property of stored energy at the membrane called membrane potential. All right, and what that is just a separation of positive and negative charge across the outer barrier of the cell. That's a form of stored energy, just like the energy in a battery, and the cell uses that to do work. Okay. Acidosis means that there's too many protons in solution and the pH is less than 7.35, and alkalosis has a pH greater than 7.45, right? And this is going to cause problems with the nervous system, the muscular system, and really all over the body in either case, okay? So the body has 3 systems that we're going to learn about that keep the pH where it needs to be: the urinary system, the respiratory system, and your body's buffer systems, okay? Buffers are simply solutions that are capable of turning strong acids or bases into weak ones so that the pH doesn't change very much. You've got different buffer systems all over the body. The urinary system responds to a low pH by making an acidic urine and you pee it out, and to a higher pH by making a basic urine that you pee out, okay? And then the respiratory system responds by either making you breathe faster or slower, okay? If your pH goes down, you breathe faster and you blow off more carbon dioxide, because when carbon dioxide mixes with the water in our blood, it produces carbonic acid, which lowers the pH, okay? And then if the pH gets too basic, then you breathe more slowly, okay? And that makes you hold on to more CO2, and that causes the pH to go back down into the normal range. Different forms of energy are shown here, right? Mechanical energy is the energy that's used to move objects, right? Chemical energy is the energy that's contained in a chemical bond, all right? It's released when the chemical bond is cracked. Electrical energy is the movement of charged particles from one location to another. Radiant energy is the energy of electromagnetic radiation, such as X-rays or UV rays or even visible light, moving through space, all right, to have an impact on a target, okay? Thermal energy is just the movement of heat from one location to another. And then nuclear energy is the production of electromagnetic energy from what we call radioactive isotopes, okay? And it's really a form of electromagnetic energy. The only source of energy that the body can understand and use right away is something called ATP, okay? ATP has energy stored in the bonds between phosphate groups, because phosphate groups have a negative charge at neutral pH, and so the covalent bonds that hold them together are very powerful. And so when you crack those bonds, the energy that comes out is used to drive work inside the cell. Okay, the other parts of ATP are a sugar called ribose and a base called adenosine. Okay, those aren't particularly important to the energy part of the molecule, but they are important for other purposes. Okay, so you might well ask, well, why is it that our cells can only use ATP? Well, we can draw an analogy sort of like your car, right? Your car runs on gasoline, okay? When you put gasoline in your gas tank and you turn the ignition and then you step on the accelerator pedal, the gas in your tank goes to your carburetor, and then your carburetor is going to inject it into your engine block, where a spark plug will make a spark, and then that mixture of gas and air will cause an explosion when the spark hits it, and that'll move pistons in your engine block up and down, and that'll turn the crankshaft, and that eventually turns the wheels of your car. Okay, and so that's an example of several energy transformations, right? There's chemical energy in your gas, right? And you turn that into the energy of pressure and heat and light when you explode it with a spark, okay? And that produces mechanical energy that turns the wheels of your car. And then there's heat lost at every step, okay? But where does gasoline come from? Gasoline comes from crude oil, which is a thick, sticky liquid that comes out of the ground. And if you were to put crude oil in your gas tank, your engine wouldn't understand how to use it. Okay, you would turn your ignition and step on your accelerator pedal and nothing would happen. But if we take crude oil and we crack it into tinier pieces, then it becomes something that our engine understands. And the piece that's in gasoline that makes your car go is an 8-carbon molecule called octane. Just like an octopus has 8 legs, octane has 8 carbons in it, okay? And it's what's called a hydrocarbon. In the body, the energy that we use is contained in what we eat, right? We eat a diet that has fat and protein and carbohydrates in it, as well as vitamins and minerals and water, right? And what the body does is it takes that fuel, and in the digestive system it mechanically and chemically breaks it into small enough pieces that we can load that into the blood supply, and then that nutrient-rich blood goes to an organ called the liver, and then the liver takes all of that fuel and turns it into either fat or into a type of sugar polymer called glycogen or animal starch. And then when the body needs energy in the blood, what the liver will do is it'll turn around and it'll take the glycogen or the fat and it'll turn it into blood sugar, which is something called glucose, and it'll load that into the blood, and then that sugar will make its way in the blood to all the tissues in our body. Our tissues will then take that sugar up, and then by cracking the bonds in the sugar molecule, it'll remove the energy from those chemical bonds, and it'll transfer it to ATP, making heat in the meantime, and then the ATP is used to do work, okay? So you might think that that's sort of a complicated way to get our energy, but we don't have the ability to directly use the energy in the fuel that we eat in order to do work. So we have to process it a little bit first, just like you have to process crude oil into gasoline before your car can understand how to use it, okay? The reason that we need ATP is because some chemical reactions that are critical to maintaining life don't happen all by themselves, okay? And these are called anabolic reactions, okay? Anabolic reactions generally involve building something large from tiny pieces. And that's not something that happens by itself, okay? That's not something that obeys the second law of thermodynamics, right? Which says that we try to get to the low energy situation. I mean, if you think about it, things don't spontaneously assemble themselves into long chains, okay? But we still need to build these things anyhow in order to maintain body function. So the way we do that is we borrow energy from an energy releasing reaction, and then we use that energy in an energy consuming reaction in order to make what we need that keeps the cell alive, right? Whether that's building proteins or building stuff like DNA and RNA or making cell parts, right? All of that requires energy to happen, right? And the energy has to be in the form of ATP, and it gets stolen from the energy in the food that we eat. Another thing that we should address is the nature of mixtures, right? Mixtures are combinations of two or more substances that can be separated by physical means. An example would be sand and water, right? That would be a mixture that could be separated simply by letting the mixture stand, right? And then the sand will settle out. Okay, it's a type of mixture. It's called a suspension. Okay, a sugar-iron mixture can be separated by a magnet that would pull the iron out of the sugar. Okay, a solution is different. In a solution, there are two parts that stay evenly distributed, and another important property of a solution is it's generally transparent. Light passes through it. Okay. The solute is the thing that gets dissolved, and the solvent is the thing that does the dissolving. Okay, you could have a solution that's a polar solution, like one that's based on water, or you could have a solution that's a nonpolar solution, like one that's based on oil. Okay, you could mix different oils together and make a solution. Okay, another type of a solution is something that's called a tincture, right? A tincture is essentially a nonpolar compound dissolved in a nonpolar solvent. An example would be tincture of iodine, okay, which is a combination of alcohol and water and iodine, which in its normal state is a molecule that's nonpolar, okay. Remember that a solution can be a liquid or a gas, all right. You can have gas solutions, you can have liquid solutions, okay. The solute will never separate from the solvent as long as there's enough solvent to cause the solute to be surrounded by the solvent. Okay, take an example, right? You can take a glass of water, and you could take a spoonful of salt, and you could dissolve that in a glass of water pretty easy. Okay, you could probably do that 3, 4, 5, 6 more times. But eventually you'd get to a point where you throw the salt into that solution and it wouldn't dissolve. And the reason is that all the water molecules are already occupied with surrounding the little ions that come from the salt that was already in there. And so what will happen to that new salt is it'll fall to the bottom of the container and just sit there. And that's called a saturated solution. Okay? So you can do this up to a point, right? And then you run out of the solvent. A suspension is just a mixture with large particles in it, okay? And a colloidal suspension are particles that remain suspended within the liquid. An example would be something like milk, okay? Precipitates are solids that form in a solution during a chemical reaction and generally settle at the bottom of the reaction vessel, like the bottom of the test tube or the bottom of a beaker, okay? And generally precipitates are salts, okay, that have a tough time dissolving in the solvent, all right? If a suspension isn't shaken continuously, the particles will settle out, right? An example of that, again, would be sand and water, okay? But a colloid, examples include milk, would be an example. Blood plasma is a colloid, okay? Blood is actually a suspension, okay? If you take blood and you just let it sit, the red blood cells and the white blood cells will settle, okay? And the plasma will remain as a colloidal suspension, okay? So blood is a more complex mixture. Most of blood is actually water, all right? If you have any questions, make sure and email me, and I'll get back to you within the day. Hopefully this has been useful for you, and I'll see everybody in the next podcast.